All right, so today's lesson is the beginning of our final unit of calculus. This unit is called antiderivatives, and as the name kind of suggests, it's just kind of like doing derivatives, but going backwards because it's an antiderivative. Anyway, we're going to get going on this one today. I'm going to give you a bit of a heads up. It's going to probably be a pretty long lesson today. I mean, if you're watching this video, you can already see how long it is. Watch as I'm eating my words, and this will be like under half an hour, but I doubt it. I think this is going to be a long one. So again, beginning our fourth and final unit. The first half is going to be pretty heavy on definitions, so there's going to be a lot of new information. Just make sure you pause if you're getting overwhelmed by any of this. You can always rewind, watch it again, but there are quite a lot of terms that come around that we'll have in the first half here. As for the second half, we're going to do a bunch of antiderivative examples. These are pretty weird. I'll let you see when we get there, but just hang tight today. You're going to see it's going to be a bit of a weird one. Anyway, let's get rolling. So before we begin, I just want to talk about the purpose of differentiation. We should probably have a pretty good idea of this at this point. We've been doing it pretty much this whole course, but I want to recall that differentiating a function can provide some very useful real-world information. For instance, suppose you had a function that modeled the height of an object as it fell over time. We can call this function h of t, the height as a function of time. Now, the derivative of the function, h prime t, or if you like using Leibniz notation, which I don't really use it too often, is dh over dt, the derivative of h with respect to time. That would provide us the rate of change of h with respect to time. This means it's a change of height over time, and that's known as a velocity. In other words, the speed at which that object would be falling. Now, the second derivative, h double prime t, or d squared h over dt squared, would provide the rate of change of the rate of change of h with respect to time. This, in this case, a rate of change of velocity, would be your acceleration. Again, none of this is really new, but it is still important to talk about what the purpose of this is, because what if instead of starting with a height, we had started with an acceleration or even just a velocity function? How could we go from those functions and find our way back to a function for height, right? This is where we have to kind of go backwards. Right? So going backwards in the differentiation process is what we would need to be doing in order to find the height function, which is a really weird thing to say. Now, the process of determining an original function when its derivative function is known is called integration. Integration is basically the opposite process to differentiation. It is just doing differentiation backwards. We're starting with a derivative and we're going backwards by using integration to find the original function. Now, the original function produced through integration is called the integral. That's going to be a very common word we use. Or you could call it the antiderivative. Now, I'm going to be honest with you. I usually say integral. Antiderivative is generally thought to be a synonym. There are some people who argue semantics about that. There's actually a difference. I'm not one of those people. It's like, it's whatever. You say integral, you say antiderivative, potato, potato. I mean, nobody says potato, but same idea, right? It's the same thing, integral and antiderivative. I'm not going to argue it right now. In Math 31, they're the same thing. So basically, you use integration to find the integral, or in other words, the antiderivative. You're just going backwards. Anyway, I'm rambling. Let's move on. So let's consider the following here. Imagine we had these three functions, f of x, g of x, and h of x. And they're all pretty similar. They all have a 2x squared in them. But g of x has +4 and h of x has -6 attached. What are the derivatives of these functions? I'm not even going to get you guys to pause the video. I'm just going to do them because it's going to go quick. The derivative of f prime, well, we can just use the power rule. The 2 here can drop down in front and multiply by the 2 that's already there, and you're going to get 4x. That wasn't a big deal. The derivative of g prime x, same idea. Use the power rule, bring the 2 down. It's going to make it 4x. And then the derivative of 4, well, it's a constant, so the derivative of 4 is just 0. So the derivative is also 4x. As for h prime x, wouldn't even be surprised if you already did this in your head just by looking at it. Take the 2 down, it's going to be 4x. Derivative of -6 is also 0. Have a look at that. All three of these functions, even though these functions were different, their derivatives were still the same thing. All of their derivatives equaled 4x. So if we had instead started with those derivatives, if I had told you f prime x was 4x and g prime x was 4x and h prime x was 4x, if we had started with those, what would the antiderivative be? Well, the antiderivative would have been going backwards to get the thing we started with. But what I hope you notice here is that all of these derivatives were the same, yet their original functions were different. These constants were kind of invisible to the derivative, right? If we were asked to work backwards, there is no way, if we didn't know that first line up here, there is no way that we would have just been able to predict what those constants are. So the first kind of quirky thing with antiderivatives that we're going to get into is the fact that when you take an antiderivative, you have to just throw in a constant. And the constant is, if it's not known and you didn't have any context to find it, you unfortunately just have to put a plus c. So again, the constant in the three previous functions were different. Differentiation, taking the derivative, destroys the constants, so they're completely disappeared in the derivative. This is an unavoidable flaw with integration. Your constant and your integral, so when you go backwards, will remain unknown unless more context is given. When taking an antiderivative, in other words, an integral, without additional context, you have to use what's called a general constant. So if we knew that f prime x was 4x, then if we took the antiderivative and worked backwards, which we're going to get into that process in a second, then we would say that f of x is 2x squared, but then we have to also say plus c. Now, c could be 0, as we saw in that last slide, right? C was 0 on f of x. We have no idea, though, so we have to just say plus c. Or, in other words, if you had any function, if you had y prime equals f prime, then therefore y is equal to f plus c. So you just always have to add a plus c. This is an easy thing to forget. Really, really, really common for people to forget to put plus c. Even I'm guilty of it every now and then. But if you do it on any kind of a quiz or anything, unfortunately, you're going to lose half a mark. So it is important to have. All right, differential equations. This is not super important, but I'll just go through it real quick anyway. A differential equation is an equation that contains a quotient of differentials, dy and dx, for instance, they're parts called differentials. So if you see Leibniz notation, even if you didn't see Leibniz notation, because dy over dx is just y prime, as long as an equation contains a derivative, it's a differential equation. That's basically all we need to know here. Now, when we talk about solving a differential equation, this is where we found all the functions whose derivative is equal to the differential equation. So in this same case here, y prime equals 4x. Again, we're still dealing with 4x as a function on this one. The solution to that differential equation would be y, the antiderivative of y prime, y equals 2x squared plus c. This plus c kind of fixes it so that we have found all, where did I put that? All of the functions that derivative was equal to. Anyway, we're not gonna worry about that right now. That's not really a hill to die on here. But this is a really important one. I'm going to put a big star right here. Yeah, I'm going to pretend that's a star. Another symbol that represents the solution of a differential equation is something called the indefinite integral symbol. That's quite the long name for it. If you just called it the integral symbol, I'd be okay with that, right? It'd be all good, right? This will be the most common way that we represent taking an antiderivative. It's this big, long, like it looks like an S that someone stretched out. That means the antiderivative, or in other words, the integral. So what this statement right here is saying is the antiderivative of 4x, and then this dx means with respect to x, is equal to 2x squared plus c, as we've been seeing this whole time. Now, just for some additional terminology, as if that already wasn't enough terminology, 4x is what we call the integrand. That is, of course, the derivative of the original function. We'll call this one's the original function. It's the OG that we're looking for, right? Now, dx, again, like I said just a second ago, dx is what we call the differential. That's not a super important term to know. Just dx is kind of acting as a pointer to say, hey, we're doing this with respect to x. In this course, I'm not going to throw you off. I just know in higher level university courses, especially Calculus 4, which again, you don't have to worry about for a long time here now, we did start taking integrals with respect to other variables that may or may not have been present there. This is kind of like implicit differentiation, but just going backwards. And that's hard. So we're not going to worry about that right now. We're just going to worry about taking antiderivatives. Okay, so this all begs the question. Did I skip a slide? No, we're good. This all begs the question, how on earth do we do these, right? That one example we've looked at over and over again where we had 2x squared becoming 4x and then vice versa. That one was already spoon-fed to us. But here's the bad news. Integration is a very bizarre, but yet still absolutely foundational part of calculus. There really isn't a definite strategy to find integrals. So I'm really going to underline that. There isn't a way of just saying, hey, first do this, then do this, and bingo, bango, bongo, you're there, you're done, right? No, unfortunately, that's not the case. With differentiation, there was. We knew the power rule, we knew the product rule, quotient rule, chain rule, all those rules that were so awesome. With integration, we don't have those. It's a really, really sad shame, and that's what makes us so much more tricky. In order to do integration, in order to find an antiderivative, you have to have a solid understanding of differentiation and a keen eye to identify patterns that would help you undo that differentiation. This is a skill. Like, this is a real skill that just needs to be built. I don't want to say it's super, super hard by any means, but it certainly can pose a challenge because it really depends on your ability to identify a pattern. Now, my biggest tip for you right now, and this is going to be as close to a general rule as we can get, and I'll build it in a little bit more in a moment, is always watch for the classic power rule. That's where you drop the exponent down and then knock it down by 1 and all that. That's usually the rule that comes into play with most of these. It's not always the case. Sometimes we have other rules that come in, but at least for these early ones, the power rule is going to be the one to check. Now, here's my little aside. This I just added in just a few moments ago, actually. I typically imagine there being an x with one higher degree than what I've got. So if I'm told to find an antiderivative of something, I just imagine that in my answer, I have an x with one higher degree compared to whatever was in there. So if there was like an x to the power of 4 inside this, I assume I have an x to the power of 5. Then I imagine I'm taking the derivative of this. Okay, I know this is quite a roundabout way, but then I imagine I'm taking the derivative. So it's like, okay, if I take the derivative of this, oh, then that must be 5x4. No big deal. Then I take this and I compare it with what I started with. If it's equal to what I started with, then wow, that's about as easy as it gets. But usually our coefficient out in front doesn't match the coefficient here. That's where you have to do a little bit of playing around and figure out, okay, what number do I have to put in front of here to make it equal to this? We're going to do several examples of this today, of course. Hopefully it'll make a little bit more sense as we go through. In a couple slides, I'll show you like a way you can kind of cheese these, but I wouldn't rely on it too much because it becomes kind of more of a crutch than anything. But I'll show you in a moment. Here we go. Anyway, just keep an open mind is what I'm trying to say here. I'm not trying to like string you out here. So here's some examples. Evaluate the indefinite integrals. I'm going to walk you through these ones. Don't worry about trying them on your own. We're going to start with this one here. This is the integral of 6 with respect to x. Okay, notice there's no x in here. It's just the integral of 6. Let's use that little tip I put before. Remember I said I typically imagine there being an x with one higher degree than what I've got. Well, we don't have an x here. So if we imagine one higher degree x in this, we can imagine that we just literally have an x to the power of 1, right? Because there's no x here. So it's like x to the power 0. So we imagine we have an x to the power of 1. If I took the derivative of that, you would end up having, well, the 1 drops down and then x becomes x0. So you'd end up just having 1. Well, that's not really too useful. So basically what we have to ask ourselves is, if this was the derivative of the x, what would I have to multiply this by to get this? Well, I think the answer to that would be you have to multiply by 6. So why don't I try going back to this step and I put a 6 in front of here. So if I say we had 6x as our antiderivative, what would be the derivative of 6x? Well, the derivative of 6x is just 6, and that's what we started with. So in other words, we can say in this case that the derivative is going to be 6x. But just wait, there's one more thing we have to do here. Remember earlier on I said when you take the antiderivative, the constant in what you started with kind of disappeared. That means what we should do for our final answer, I'm just going to avoid all this stuff here. I'm going to put equals. It's going to be 6x, but then we also have to say plus c. Because if we were to take the derivative of this, since c is just a constant, the c would vanish and we'd be just left with 6. So the bottom line is here, when we're taking the antiderivative, or in other words, when we're taking the integral, we want to come up with some sort of function that if you took the derivative of this, it gave you what you started with. Let's try another example. The antiderivative of x with respect to x. So we'll try my little strategy. That's a horrible arrow. We'll try my strategy here. Start with a degree 1 higher than what you got. So I'm going to start with an x squared. If you took the derivative of x squared, that would give you 2x. Well, let's compare this with what we started with. What we actually started with was just x. So I think the real question is, what would we have to multiply 2x by to turn it into x? Well, I think the answer to that would be you have to multiply it by 1/2. So let's go back to the drawing board here. Instead of 1x squared, we'll make it 1/2 x squared. If you took the derivative of 1/2 x squared, the 2 drops down, it knocks out the 1/2, and you're just left with x. Well, notice now, that's what we started with. Perfect. So in other words, this 1/2 x squared must be our antiderivative. Long story short, though, we're not supposed to just leave it on its own. We always have to add a plus c. So we're going to say this equals 1/2 x squared plus c. Now, there are going to be certain situations later on. We're not going to worry about it for today, but there will be situations later on where you will be able to solve for c. But I would have had to tell you some additional context to this. Like if I told you, oh, if you plug in, x equals 4, it equals this, or whatever, and then you could plug it in and find for that. But we're not going to worry about that for now. Let's just worry about always remembering to plus c at the end. All right, here's a couple more indefinite integrals. If you really, really, really want to try, you could try these on your own, but I'm going to warn you that second one here is in particular a little bit more challenging. I'm going to go over them though, one way or another. So just showing my mental strategy I use here, and keyword there being mental strategy. I don't usually, when I solve these, I don't usually write out literally every step of my thought process, and I don't expect you to either. So what I would say is instead of x squared, when we take the antiderivative, it's going to be something that has an x cubed in it. But if I took the derivative of x cubed, that's going to give me 3x squared, which obviously doesn't match what we had. So I ask myself, what would I have to multiply 3x squared by in order to turn it into just x squared? Well, I think the answer to that is you'd have to multiply it by 1/3, or in other words, you'd have to divide it by 3, whatever floats your boat on that one, right? So instead, going back to the drawing board, we'll say it's 1/3 x cubed. Now let's see if that derivative gives me what I want here. If you take the derivative of that, you're just left with x squared, which, boom, that's exactly what we want. So this 1/3 x cubed is my antiderivative. So I'm going to say this equals 1/3 x cubed, and then don't forget to say plus c. Okay. The nice thing about this is they're quite easily checkable. Like you could always just say, you know what, this is my original function now. If I take the derivative, did I get it right? The hardest part about this, though, is identifying the patterns and seeing where you can go from there. All right, next one here. The antiderivative of 5x cubed. Again, start with my basic strategy. I'm going to say, all right, I'm going to start with x4. If you took the derivative of x4, you have 4x cubed, but we are actually supposed to have 5x cubed. Now, you might be tempted just to say, oh, well, we just need to add an x cubed to that because 4x cubed plus 1x cubed, that's 5x cubed. But no, you can't add anything to it because if you added something to it, that would change your whole derivative. That's a whole gong show. So we have to think about what we have to multiply by. So remember what I said, especially on this last one. It was a little easier to see with this last one, and I'll explain why I'm doing the last one here in a second. If we looked at this 3x squared, remember I said 3x squared multiplied by something equals x squared. Well, the logic behind that is that way you can just kind of solve for this by dividing by 3x squared on both sides, and you can say, okay, then that question mark, if you divide by 3x squared, must be 1/3. By that same logic, let's ask ourselves here, 4x cubed multiplied by something needs to equal 5x cubed. So if we divide this 4x cubed away, you're going to find that we have this something that we're multiplying by. The x cubes cancel, must be 5/4. That's certainly a weird one, but it is actually pretty normal for us to have some crazy fractions and all this. But anyway, let's try it again. So this is the number we need to multiply by. So if I go back to the drawing board here, 5/4x4. If you take the derivative of that, you're going to end up having, I guess the 4 is going to drop down. That's going to knock out the 4 on the bottom, and you're going to be left with 5x3. Perfect. That's exactly what we wanted. So therefore, the 5/4x4, that must be our antiderivative. So our answer is 5/4x4 plus c. Now, you might start noticing a pattern here. In this last example, we bumped up our degree to 3, and we ended up having a 3 on the bottom of a fraction that we used as a coefficient. In this one, we had 4 as an upgraded power here, and we had 4 on a denominator here. That's not really a coincidence, and that kind of leads us into a generalized rule. Now, this slide, if you just looked at it without really breaking it down, probably looks like an absolute unmitigated train wreck. And I don't blame you for this, but let me hopefully help break this down for you. If you want a generalization for this, the closest we can get to having an actual, okay, do this and then do this kind of follow it rule is the antiderivative of x to the power of n, where n is just any number, with respect to x, of course, is just going to equal x to the n plus 1, so one higher power one higher power, divided by n plus 1. So whatever the value of that higher power was. And then, of course, plus c, right? Constant. That's basically what we've been doing here. Now, some of the examples like that last one, though, we had like 5x cubed or whatever is what we started with. Well, that's where we can actually be quite fortunate. This generalization can be extended to when there's a coefficient in front of the integrand. So if we had ax to the power of n, the a can just come out of the integral, because a, when it's multiplying by some x that we're taking the derivative or the integral with respect to, the a is irrelevant, just like it was when taking the derivative. So it can come out and do its own thing. And then we can just have it chill on the outside just like that. If you like this method, it works quite well just as a general rule. But like I mentioned a couple minutes ago, I don't want it to form a crutch for you. Now, for the most part, this will work just fine. It is great to think of it this way. But sometimes when you're not dealing with like a power rule question, this can end up kind of doing more harm than good. Because oftentimes you will be forced to think of it in this regard rather than thinking outside the box and potentially seeing some other strategies of doing this. Again, we'll build this as time goes on. We're just starting with the basics today, but here we go. So using whatever method you want, let's take the antiderivatives of this. I know these are higher power ones, but it really doesn't change much what we've been dealing with. I would appreciate it if you just pause the video here, give these questions a try, and I'll go over them in a second. All right, so I'm going to go over these now. Hopefully you were able to solve for them. The good news is, of course, you can check your work pretty easily. If I take the antiderivative of this, I'm not going to show as much work as I used to. I just know it's going to be x to the power of 11 is what I've got here. But if you brought the 11 down in front, you'd have 11 x to the power of 10, and that's no good. So I'm just going to divide it by 11 and then plus c. So again, you could always check this by taking the derivative, and you'll see the 11 comes down, knocks down with the 11 on the bottom. We have x to the power of 10. Whatever floats your boat, though. That's how that one's done. Same with this one here. We're going to have an x to the power of 5. Notice how even like when I'm not showing my whole thought process, I always start just by writing that down. If we took the derivative of this, I'm just going to like think on this. The 5 would come down, so we'd have 5x4. That's not enough, though. We would need to multiply this by 4 to begin with, because when you take the 5 down, 5 times 4 gives you the 20 we want, and then that drops down to a 4. So it's going to be 4x5 plus c. Again, for that second one, you could have always used this strategy. If you use that strategy instead, you would have had just 20 times x5 over 5 plus c, or in other words, 20x5 over 5 plus c. 20 divided by 5 is 4, so 4x5 plus c. It gave you the same thing one way or another. So again, that crutch, it can work, but it just works for only power rule questions, which again is fine for when it comes around. But whatever floats your boat, I don't mind. All right, what about this one? Evaluate the integral of p cubed with respect to p. Okay, well, it's just literally throwing a different letter in here, but the good news is it's still with respect to that letter. So the fact it's on x here doesn't change anything. This is the same as what we had before. You can pause and give this one a try if you wish. Otherwise, I'm going to go over it right now. So again, the antiderivative of this, I'm not even going to show all that work that I did before. I know it's going to be p to the power of 4. But if I took the derivative of this, that'll make it 4p3. Well, I don't want that 4 there, so I'm going to divide by 4 to get rid of it. So if I took the derivative, the 4 comes down, knocks out with a 4 on the bottom, and we just have p to the power 3, which is what we want. But don't forget, we have to add c every single time, because otherwise we don't have all the possible answers. We only have one possible answer if we didn't say plus c. All right, here is where our power rule dies. Okay, we're taking the integral now of cosine x. Remember earlier on I said in order to take the integral of something, you have to have a really strong understanding of taking the derivative. Here's where that is really exemplified here. If you try to use the power rule on this, you are out of luck. There's nothing we can do on this with power rule. Instead, you need to know your trig derivatives like the back of your hand. Now, the good news is you do have a formula sheet in this course and you can use it on this one. What we need to ask ourselves is if we're taking the antiderivative of cosine x, what we really should wonder is what function taken to a derivative equals cosine x. Well, here's the thing. I can tell you right off the bat that I know sine and cosine are linked by their derivatives. I know the derivative of sine x, how would I say d over dx? The derivative of sine x is cos x, and I know the derivative of cosine x is negative sine x. Notice we're going derivative this way. If we're going to go backwards, we can see that since we're starting with cosine x and we're going backwards, we can reasonably say that the antiderivative of cosine x is therefore positive sine x. But here's what's weird. We have to still include the plus c, because if we just had sine x, that wouldn't be telling us the full story. The plus c tells us that there could be any other number attached to this, as long as it's just a number like 0, 1, 2, or negative 4.5 or whatever, right? Just some number. That's what we're dealing with right here. So in terms of work, not really much to show there. And you're going to find that with integrals, there's often not a lot of work that you have to show. But the hardest part is just wrapping your mind around these. Integrals take quite a bit of brain power. So if you find yourself sitting and just thinking on it for a while and feeling like the gears in your mind just turn and turn and turn, that is totally normal. I had a university professor for actually one of my highest level math courses. And I always remember he was embarrassingly bad at integrals. He would often like stop even on some of the more basic ones and be like, okay, hold on. And he'd have to do them in his head pretty quick. But yeah, so in other words, what I'm trying to say here is it's normal for you to struggle with these. It does take quite a bit of back end thinking here. You have to really be thinking deep in your mind. All right, here's another example. This is the integral of the cube root of x. Oh my goodness. Okay, this one's going to be tough. I'm not going to get you guys to try this one on your own unless you're really, really brave. So I'm sure you would have paused by now if you wanted to. What I would say, though, is instead of dealing with a cube root, just like when we were taking the derivative, let's change that to like an actual exponent, because remember, radicals can always be written as exponents. So instead of this, I'm going to write this as the integral, not of the cube root of x, but of x to the power of 1/3. And just remember, the cube root is, 1/3 is a power, just like a square root is 1/2 is a power. And I should remember dx. So now that that's a power, we can use that rule that I established before. As a matter of fact, if you really wanted to, I'm sure you could even use the generalized rule that we established, the one that I call the crutch. I'm not going to use that, though. I'm going to go crutches free here. If I increase this power by 1, that means I'm going to have x to the power of 4/3, right? Because 1/3 plus 1 full whole, 1, right, is 4/3. But if I took the derivative of 4/3 or x to the power of 4/3, I'm actually even going to show my work here just to really list this out. If I took the derivative of this, that would give me 4/3 times x to the power of 1/3. Well, we don't want this 4/3 here. So it's kind of like we have to divide this by 4/3 so that when the 4/3 comes out, it gets rid of this with this divide by 4/3 we started with. Now, here's the thing, though. We don't like having a fraction inside of a fraction. It just looks miserable. And you might say, oh, well, who cares? It's still an answer. Like, this is still an answer. It still works. But we shouldn't have a fraction inside of a fraction. So I'm just going to do keep change flip on this one because we have a fraction. Technically, this is over 1 on the top, divided by a fraction. Just to show all my work on this one, that's x to the power of 4/3 over 1 divided by 4/3. You got to keep the top, change the bottom, or change rather the divide to a times, and then flip the bottom. So what this will give me is 3 times x to the power of 4/3 over 4. And then we should, of course, say plus c, because when we take the derivative of this, we still need to have a plus c in there as well. Now, I would accept this as an answer. This is totally okay, but some people are just like really stringent rather on their exponents that are fractions. Some people just really don't think that's good. So instead, if you wanted to, you could turn this back into a radical. It doesn't take any real amount of time here. So we'd say this is 3. Instead of x to the power of 4/3, we would say it's the cube root, because the denominator is 3, of x to the power of 4. Remember, the numerator is the power on the radicand, and the denominator is the index of the root. And again, that's all over 4, and then plus c. That's probably a better answer, not going to lie, but I'm fine with a fraction exponent. I'm just not fine with this. That over there, that's a no-go. You can't sell that. But those other two, the ones I put in boxes, those are just fine. Totally okay. Last thing we're going to cover here today is sum and difference integrals. Believe me, this is the last thing. Don't worry. If you're integrating the sum or difference of a bunch of functions, it's usually easier to integrate them separately. So in other words, if you have something where it's a bunch of things added together and you're integrating the whole thing, just split it apart into chunks. It works for addition. It also works for subtraction. So maybe I should say plus or minus. But what it doesn't work for is multiplication or division of functions. With those, you can get creative with product rule and quotient rule, or in all honesty, you could just expand it out because that would probably be easier. but we're not going to worry about those for now. Sum and difference integrals, though, that does come around quite often, actually. That's pretty standard stuff. So we'll do just a single example, at least I think. Yeah, just a single example here. Take the integral of 3x squared minus 10x plus 11 with respect to x. If you don't mind, I'd like you guys to give this a shot on your own. So if you could pause, just make sure you're breaking this apart. Anyway, I'll go over it in a second. All right, I'll go over this now. So like I said, take this into little pieces, right? So we'll say it's the integral of 3x squared with respect to x minus the integral of 10x with respect to x plus the integral of 11 with respect to x. And yes, you need to put this dx on all these because we're still integrating with respect to x. Every single integral sign needs to have a differential with it. You have to say what that dx is or whatever you got, right? Now that we've split this apart, let's just solve each of these separately. For the integral of 3x squared, remember what I would usually say is just say, look at the power one higher than what you got. So this is probably going to equal x cubed. But if you took the derivative of x cubed, you bring down the 3, that gives you 3x squared. Oh, wow, that actually worked all in one go. That was actually really nice. Okay, so yeah, the integral of 3x squared is x cubed. Awesome. Now, usually we'd say plus c, but because we're doing all of these, we're just going to combine it into one big plus c at the very end. So I'm not going to put a plus c here yet. I'll just put a plus c on the end because all those c's can combine into one because they would all be technically like terms if they're all just numbers, right? Minus 10x, the integral of that, well, I know it's going to be something with an x squared. If I took the derivative of x squared, that would be 2x. We don't want 2x, though. We want 10x. So what would we have to multiply 2x by? We have to multiply it by 5. So I'll put a 5 out in front. If we just check this one more time, the derivative of 5x squared would be 10x. That works exactly what we wanted. Perfect. Plus the integral of 11. I'm not going to, play any tricks on you here. Remember before with the 6 one, I was like, it's an x something, and I played around with it. Honestly, guys, if you take the integral of a single number like 11, it's just going to be 11x. You just toss an x on there. That's all that's going to happen every single time. Those are really nice ones. Okay, I'm not gonna play around. Anyway, like I said before, though, each of these have a plus c. All of those plus c's are going to add together. It's just going to be one big plus c. It's not plus 3c. Don't go crazy on that because all three of these could have different c values. So we're just going to say plus c as a general constant. Bingo, bango, bongo. Done. Whew. Okay, amazing. Now, at the beginning of the lesson today, I said, oh, I'd be surprised if it's anything less than half an hour. We were pretty darn close. We're just over half an hour here today. That is actually really impressive. I'm surprised how quick we got through that. But for practice, I want you guys working on indefinite integrals practice. It's the very first sheet in the new integrals work booklet. I did give you one before classes canceled out, but if you didn't get that home, there is a digital copy, of course, on Google Classroom. Just a bit of a heads up, this one isn't from my regular resource, but no worries. I've included the answers on the back of that first page. They're just down at the bottom, so you have some work room. Anyway, if you have any questions or if you need any extra help, please come and ask. Best of luck.